Hi, I'm Moitreya. I'm a research scientist with the computer vision group, as Shashwata mentioned earlier, at MERL. And today I'm happy to present our work titled Gear-NeRF, Free Viewpoint Rendering and Tracking with Motion-Aware Spatio-Temporal Sampling. Now, I understand that this is sort of a broad audience here, and not everyone is from the 3D sort of computer vision community. So I'll try to gloss over some of the low-level details, but then I hope to convey the key contributions that we make in this work. This is a joint work with Shinhang Liu, who is a former intern at MERL, and my colleagues Suhas Lohit and Pedro Meraldo. And this appeared at CVPR this year. You feel free to check out more about our work at this link that's shown here. So the task that we seek to address in this work is that of novel view synthesis and tracking. So given a scene that has been captured from multiple views, such as the one that's shown here, using Gear-NeRF, we hope to be able to render this scene from a new view. So from a view that is not the scene has not been captured from. And so as you see here, the scene is kind of tilting and it's basically being rendered from different views. And so essentially we are rendering, I mean, for each of these tilted thing is like a new view that we're rendering the scene from. And additionally, what Gear-NeRF allows us to do is, given a particular region of interest in the scene, such as this person, and if an end user were to click on the region of interest using a mouse, for example, Gear-NeRF can actually track that region of interest in the new view. So because the click was on the person, so we see that the person is being rendered from a new view over time. Now, this has wide-ranging applications, of course, including in augmented reality, virtual reality, 3D modeling of articulated objects, game playing, and so on and so forth. Yeah. I mean, the whole Oculus and all of this, right? So before we delve into the details, let's sort of go over some preliminaries, which these are basically some tools that we're going to use as part of the method. Yeah, so let's just quickly go over them. So the first thing that we might talk about is the segment anything model, which is essentially a method proposed by Meta last year. And it's one of the state-of-the-art approaches towards segmenting an image. And by segmenting, I mean basically grouping pixels semantically. So if you were to look at this image here, the one that I'm pointing at, you might say that, you know, all these pixels that lie on this aeroplane should actually be grouped together semantically. Or if you were to look at this image, all the pixels that correspond to this ocean kind of a thing should go together, and so on and so forth. Now, different from a standard segmentation model, which just segments the whole image, SAM can actually do a targeted segmentation. What do I mean by that? So maybe while we're given this whole image, what might be of interest to us is not the full image, but only parts of the image. So if an end user were to provide prompts such as through mouse clicks, through a bounding box, through a mask, or even through text, SAM can actually target or orient its segmentation, you know, according to the prompt that's provided, right? And what it does is basically it employs a transformer architecture, which has an encoder decoder kind of a setup, right? And in the encoder phase, an image that we want to segment is actually encoded into a feature space. And then in the decoder phase, that encoded feature is coupled with the prompt that sort of guides the segmentation process to yield the segmentation mask that is of interest to us. And the point to remember here is that this output of the image encoder is actually also uh, a feature map. But then that feature map is in the form of it has a 2D spatial layout to it as well. So you can think of that as an image as well in some ways. It's not an RGB image; it's a image of features, but it still can be treated as an image. Um, and SAM kind of is trained in a supervised way. So basically, I mean, the way it was trained is it was shown many millions of images, and for every image, it had many segmentations of objects of interest, and I think it's in the order of billions, for example. And you kind of, if you do an accurate job of the grouping, you get a low loss. While if you don't, you get a high loss, and you backpropagate the gradients and you update the model. So that's sort of the setup. Another tool that we're going to use is neural embeddings. I mean, I'm sure that a lot of work in NLP and all goes on at the school here, and so I mean, you're all familiar with this, but just to kind of recap, so discrete data, such as text, for example, uh, is hard to directly represent in a continuous feature space, right? Because there is no inherent ordering between them. You don't know if War and Peace should lie to the left of Anna Karenina or to the right of it, or things like that. And there's also no notion of distances directly. So is War and Peace more similar to Anna Karenina, or is it more similar to The Hitchhiker's Guide to the Galaxy, right? uh, to get these sort of notions, or to embed these notions into this kind of data, what one needs to do is actually to convert them to vectors. So neural embeddings, what they do is they take such discrete data. It's kind of like a lookup table. So it maps a discrete data to a feature vector, in this case a 50-dimensional vector. And so each of these things, in this case names of novels, if they can be embedded into a feature vector, then you can do all these things like have a notion of ordering, have a notion of similarity, and so on and so forth, right? Now, the way we are going to use this is not necessarily in the context of textual embeddings, but we're going to use them in the context of coordinate or grid embeddings, right? So we're going to say, okay, what is the embedding for coordinate 1, 1? What is the embedding for coordinate 3, 5, and so on and so forth? And we'll see in a moment how that gets used. But that's sort of the idea. But the point being that be it Cartesian coordinates, or be it names of novels, discrete data like these can be embedded into continuous feature vectors, like through a neural embedding, essentially. So yeah. So now onto the core problem that we are addressing. So I mean, NeRF was kind of like a breakthrough approach in the novel view synthesis space. This work appeared in 2020 at ECCV that year. Um, and what it does is essentially, given any 3D point XYZ, and the viewing direction is just a way to denote where you're viewing the scene from. So whether you're viewing it from this point of view or from this point of view. So given any 3D point, such as this dot here, and the viewing direction, what would be the color? What would be the color of that point? When you view it from that point of view. Now, to do that, what NeRF is doing is it's essentially learning a multi-layer perceptron, f theta, sorry, um, and it's mapping this to the color of this 3D point when rendered from this view. But it's also spitting out a density value. Now, what does density mean here? Density is just a measure of how much light can go through. So if you are to trace a ray from this viewing point through the pixel into the 3D space, you like not everywhere in the 3D space do you have equal density of mass present, right? So for example, if this region is like air, essentially, you would have most of the light just go through it. But then if you hit this, if the ray hits this Lego set, then the ray kind of gets blocked. So it can't propagate any further. So that would reflect in the change of density. So the density here would reflect that most of the light goes through, while the density on the Lego would denote that most of the light is blocked, essentially. And this NeRF is essentially learning a implicit 3D representation of the scene. So if you do this, meaning that if you do this, if you learn this 3D to color mapping for enough number of points, you essentially have learned a way to render the whole scene, whole 3D scene from any given viewpoint. Um, And this just sort of lays out that that mechanism, this in a figurative kind of a way. And this is a more architectural representation of this. So given any point x, what I mean, I'll gloss over the details, I guess, but there are things like positional embedding that needs to be added to 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 sort of encode this into a vector, and then you pass this through this MLP, and you at the end of it get the color and also the density. Now, the previous thing that we talked about, I mean, the classical NeRF thing was fine and good, but then the catch was that the scene wasn't changing over time. So you always had this Lego in this kind of an orientation, for as long as it can be. But then what if the scene were to be dynamic? So meaning over time it's changing. So for example, this grasping arm is kind of lowered over time, right? So now there have been approaches to address this problem as well. And in particular, there is this paper that appeared in I think a couple of years ago called Gear-NeRF, which kind of adopted a two-step approach towards solving this problem. In the first, what is done is essentially a warping function is learned. So okay, so the core idea of DNeRF is to map all these 3D points that we are talking about, these XYZs. But then here there is a time component to that as well, because you would be sampling them at a particular time step as well. So all these 3D points, X, Y, Z, T, are mapped to a common space first. Okay. So let's say a particular time instance like t equal to 0 or t equal to 3, something like that, right? And once you map all the points to this common time step, then it essentially boils down to like rendering a static scene, right? It's like you take out the motion factor by mapping everything to the common space, and then you do the rendering in this from this common space to the new view that you might be interested in. Um, Now there have been advancements on this as well, and one such advancement appeared in this, I mean, paper called Hexplane, I think in CVPR last year, um, where basically this instead of learning an explicit deformation field, what was being done in this paper was essentially, I mean, a direct neural embedding, the one that we just talked about, is learned of this 4D space. 4D because it's XYZ and time. And there is I mean, not like the embedding learned is not directly a mapping between XYZ to a vector, but it's kind of factorized in some way. And I'll talk about the details of it in a moment. But then the reason this was done is because this was more fast. And also it turns out that this turned out to be slightly more accurate as well. So let's delve into this second method of kind of factorized representation, neural embedding based representation a little more, because that's what Gear-NeRF is based on. So again, just to kind of recap the setup. The setup is given any 4D point xt. X is a bold X here, meaning it's a vector of X, Y, and Z, the 3D dimensional coordinates and time, and D, which is a shorthand for the viewing direction. What we want is an output which shows the color and the density of that point. Now, to do this, what is done is essentially we will leverage neural embeddings, but then the neural embeddings are factorized. Okay, so instead of learning a 4D embedding, meaning XYZT to a vector, what we do is we kind of, I mean, and this is based on prior work. So what the authors here do is they factorize the 4D space into these planes. So XYZT, XZYT, and YZXT. Okay, and for each of these factorized planes, they actually learn the neural embedding. So within this plane, they actually learn an embedding, like 1 1, where does the coordinate 1 1, what vector it would map to, where does the coordinate 1 3, what vector does it map to, and so on and so forth. um, and once you get these embeddings, of course, you can do all the standard vectorial operations on it. So what they do is they kind of do a Hadamard product between them, and then they actually do a linear embedding. So essentially multiply that resultant vector with a weight matrix. And to get color and density, which is the final output, we just pass this resultant vector, which is the output of this computation, through a MLP, a multi-layer perceptron, to get the color and density. Now, once you get the color and density, you can actually render a pixel, because what you can do is you can integrate along a ray. So you, like I showed in the figure earlier, you extend a ray from the viewing direction into the 3D space, and along that ray you just integrate the color times the density at every point. And once you sum them up, you can get the color value for a pixel, such as the one shown by this brown patch here. And of course, once you get the approximation of a pixel, you can actually compare it with the true color of the pixel, which is available from a given view, right? And if you compute a difference, you can get a loss. And I mean, we're all familiar with deep learning, and you can backpropagate the gradients based on this loss. Now, an approach appeared more recently called hyperreal, um, and that sort of sought to marry the best of the both these worlds, right? So what they were saying is, we're neither going to adopt the entire hex plane setup, meaning this entire factorization setup, because to learn this factorization, for all the four dimensional coordinates is a bit computationally expensive. But at the same time, they're going to avoid the challenges of this approach called DNeRF, which was trying to learn a deformation from any random time step to a common time step. Because imagine if you have a very long video, and you're trying to map or estimate the deformation that has happened for a time frame that's like very far into the future, into the current time step, for example, right? Like think like 200 frames or 300 frames, something like that. So once you get into that sort of a long range territory, the learning this distortion becomes very, very difficult. So what Hyperreal does is it marries the best of both of these worlds. So what it does, it basically selects keyframes uniformly. So like every 10th frame is, for example, treated as a keyframe. And then what it does is kind of like DNeRF. It would actually map any kind of any frame to the closest keyframe. And so this is like the 10th frame. So you're only warping between 10 frames, so to speak. While But then once you get these deformation into these keyframes, you are still left with a set of keyframes. Now to render these keyframes, they actually employ the factorization technique that we talked about. So that's sort of the idea. Now, however, while all these methods exist, there exist some limitations of these methods. In particular, when if you have just one object moving in the scene, these approaches may be fine, but then there is no notion of differentiation of scales of motion. So like if you have two or more objects, like maybe one object is moving faster, another is moving slower. So like how do you adapt the whole method based on that is not something that these prior methods deal with. Also, if you have not enough views given to you, so think of the thing like kind of like a sparse representation scene of the scene, right? Well, then it becomes hard to learn the rendering to the new view. Chances are the model would overfit and it wouldn't work. Also, there is no semantic understanding of the scene. So we saw just a little while ago that inherent to these NeRF-based methods is the notion of sampling, right? And if you have to sample, well, then what is the best that you can do without any knowledge of the scene? You would probably sample uniformly, right? But then it doesn't make much sense to like sample in the vacuum. So for example, if there's a part of the scene where not many objects exist, well then that part of the scene is likely not going to change over time much, right? So there's not much of an incentive to sample there, right? So to gain that kind of an insight into the scene, you need a semantic understanding of the scene. So in this work, we're sort of going to address these points. So we're trying to we will try to get a semantic understanding of the scene, and basically to improve the sampling component, and also kind of differentiate the scales of motion of different objects in the scene, um, so as to be able to better render them, or adapt the model towards rendering them in a slightly better kind of a way. However, the sparse view setting is still something that we don't address and we leave for future work. So the core contributions of Gear-NeRF are as follows. So we use an image segmentation model, in particular SAM, to segment the scene based on the extent of motion. So what Sam was doing, the original use case of Sam was to just group the scene based on semantically. So all aeroplane pixels came together, all runway pixels came together, all bush that's in the background, those pixels might come together, and so on and so forth. But what we are trying to do is we're trying to segment based on the extent of motion. So all objects that are moving at an equal speed kind of get clubbed together into one group. Things that are moving faster than that get clubbed together into another group. Things that are moving slower or not moving at all would be like another group. And this would help us perform better sampling, and so we hope to be able to do that. Now, by employing this kind of by employing Gear-NeRF, what we are also able to do is there is no need for this velocity estimation network. So recall that in Hyperreal you still need it. Hyperreal is was the existing state of the art method for this task, um, and it had this velocity estimation network which was estimating the deformation, and then it was having it used a embedding kind of an approach to map these keyframes into a color space. But then we, in our approach, we kind of get rid of this deformation aspect or the velocity aspect altogether. And additionally, as almost like a side effect, if you will, our approach can also track objects of interest in the scene from the new views, like I showed in the first slide. So onto our model now. So at a very high level, our model has two main parts to it. In the first, we are learning this mapping from given any 4D point, XYZ, and time to density and color, just like any NeRF or novel view approaches would do. But then also we're spitting out the segmentation of the whole scene that we're rendering. Um, and using this, we can, once you learn this mapping, you can obviously get a rendering of the scene from a novel view, but also our approach allows us to track selectively objects of interest in the scene. So if one were to click on this human, for example, we can actually selectively see how the human moves over time. So that's kind of the high level idea. In particular, um, so what we do is we kind of stratify the representation of the scene into levels, or n gear levels, based on the scale of motion of a given scene. So depending on the scale of motion, we're kind of going to group the scene into regions, depending on how fast they are moving. And instead of a single 4D feature volume, so just a quick recap of the equations again. So this is the 4D representation volume we're talking about. And what you see is given any XYZ t, uh, you can always, they always have the same embedding function that they're using to render the scene. But then what we are saying is, well, we don't necessarily have to have the same kind of neural embedding, agnostic to the semantics of the scene. Instead, we can actually um, group the scene based on the extent of motion and learn a different embedding depending on the extent of motion. And in particular, what we'll do is we'll have shared representation in the spatial domain. So, factorizations which are entirely spatial, like XY, XZ, YZ, those would be shared across the different gear levels. But then the spatio-temporal factorization, so like ZT, YT, XT, those would be different for different gears. So you might have a more dense kind of a embedding, essentially learned for higher level gears, which capture regions of the scene which are moving faster, and you would have a more sparse embeddings learned for regions of the scene that are not moving or moving very slowly. Now, to do this, you will of course have to map every 4D point, xt to a gear level so that you know which embedding to use, right? So to do that, we kind of learn this gear assignment function, which is again a similar, like, another embedding function. So just with the coordinates, you can map them to a gear level value, right? So given any 4D point xt, this function is just mapping it to a corresponding gear level value, which is just an indicator of how fast that particular region around that point is moving in over time in the scene. And this is just a way to kind of round it off and get a like a integer value corresponding to it. And once you do that, you can actually use this feature embedding that you get. Uh, you can integrate it just like you do in a standard NeRF to get the color value of the scene. Now this will give you a rendering for the RGB part, but we can also do the same thing for the SAM part, right? Because um, recall that as I showed here, our network, different from a standard NeRF, can not only spit out the color, but it can also spit out the SAM segmentation encoding as well. So to derive the SAM encoding, we kind of adopt a similar approach, where we compute this FSXT, where FSXT is again obtained by summing these factorized embeddings and then mapped through multi-layer perceptron to obtain the color. And we use a MLP to map again this resultant embedding FSXT to the corresponding SAM feature map. And you can again get a loss by comparing the estimated SAM feature map with the ground truth SAM feature map, which is obtained by just passing that image through the SAM encoder. Um, and by this image, I just mean a training view. So like given given let's say 10 training views, what one would do is one would like hold out, let's say, one of the views and train the model with 9 of the views, for example. And then for the 10th view, you just render the SAM feature map, which, like I said, is a spatio-temporal feature map. So it has a spatial component to it. So it's like, it looks like an image almost. And you can compare that feature vector, I mean the spatial feature to against the ground truth feature that you get by directly passing that held out view through a SAM encoder, and you can get a loss. And you can do the same thing for the RGB as well. And that would be the resultant thing. So so like a little bit more about the gear assignment, I guess. So the total loss is essentially nothing but a sum of these photometric loss. So that's the first term, which is just a measure of how accurately one is rendering the color or the RGB part, and the SAM loss, which is the how accurately you're reconstructing the semantic uh, aspect of the scene. And what is done is we actually patchify the scene. Patchify meaning we just like split the scene into, like, rectangular patches, and like, render it like in a rasterized kind of a way. So we divide it into rows, and for every row we slice them, so that they become patches of fixed size essentially. And we choose the top k highest patches, um, highest meaning highest in the sense of the highest loss. So what we want to do is at every step we kind of want to improve upon the most lossy regions in the scene, right? So we first do, like I said, in that setup, you train with 9 views, you predict the 10th view, and in that 10th view you look at what regions in that rendered view, in that 10th view, are most lossy. So those would be the highest patches. So you take the top k such highest or the most lossy patches, and also incidentally you need the most accurately reconstructed patches as well, and provide them as prompts to a SAM encoder, right? So like I said earlier, that SAM kind of is a guided segmentation technique. So you can provide these patches as guides to the SAM decoder, and it will actually predict a mask for which region is the most lossy. So what we see in this figure here is, upon rendering, we find that first you have this horse head, which is the most lossy region in the scene. And so what you do is you kind of upshift the gear of it. So you say that, oh, I need to do a better job of rendering this horse region. So what I would do is I would, and the hypothesis is that the reason this region is most lossy is because this region has the highest motion, right? So you start by assuming that no part of the image is, or the scene is moving, and then you incidentally find out that this horse head has the highest loss. And why does it have the highest loss? Because it's moving the fastest. And then so you change the sampling a little bit, and I'll talk in a moment about how to change that. So you tweak the sampling part, and you do a little better at rendering this horse part. And so you then move to the next step, where again you compute the loss, and you'll see that incidentally the horse head again is the worst rendered part. And so you readjust the sampling again, and you move to this step where you incidentally find that now the horse kind of is being rendered accurately, but it's the person that's not being rendered as accurately anymore. So now you adjust the sampling around the person region, and you compute the rendering part that way, and you keep doing this till you get a satisfactory kind of rendering for all regions in the scene, and you stop at that point. Okay, so so I was kind of talking about this changing the sampling part depending on which region is the most lossy. And so what does that mean actually? So what we do is we adjust the spatio-temporal sampling resolution. In particular, what we do is for regions that are in the low gear, meaning not moving as fast, we kind of have a very low sampling of those regions. So the point being, like, imagine a static region, or like a background, like a wall or a bush in the background, if you're in an outdoor setting, for example. um, no matter, I mean, for most settings, these backgrounds won't change over time. So you don't need to really look at the spatial um, arrangement of it as closely. I mean, because it's not changing over time. I mean, you need enough resolution to capture the texture on the region. But once you do that, you don't need to worry about how it's evolving over time. Um, this is spatial configuration, and so you can kind of stick with a low resolution sampling there. But regions which are at a higher gear, meaning they're moving very or changing very fast over time, like the head of the horse, well, then you would actually need to sample more densely in that region, because um, those regions, the spatial appearance of those regions would be evolving very fast. So if you have more samples in that region, spatially, you would actually be able to render it more faithfully. Now you need to do that same thing for the temporal aspect as well, because a low gear region, meaning again a low motion region, doesn't change over time as frequently. But then a high motion region changes over time quite frequently. So recall that KG embedding thing that we talked about. So there is that time component to it, that I showed right here. This thing. So it is a spatio-temporal component. So this spatio-temporal component, like how densely you're sampling, or rather how dense of an embedding you're learning, that can be tweaked based on the gear level. So that's the G here. So if you have a higher gear level, you sample more densely on the time axis. If you have a lower gear level, you sample more coarsely. And that's it. So with that, you can kind of get a more accurate rendering of the whole scene, and that's pretty much our method. Um, Now, additionally, like I said, we can also get a novel view rendering of regions of interest in the scene. So, for example, if the user were to provide a click on, let's say, the person, indicating that that is the region of interest, what we can do is we can trace a ray from the viewing direction of the user and into the 3D space, and basically look at how the density is distributed into the 3D space. So of course, more objects are present in some regions along the ray, and less objects are present in some regions along the ray. So you have this kind of a varying density as you go along the ray. And what we do is we look at the first 3D coordinate, which has a density of greater than zero. Actually, in practice, we use a small threshold, not zero. But the moment you encounter a point which has a reasonably high density, let's say, that is kind of suggestive of an object existing essentially. And we kind of the working hypothesis is that that is the object that the user is interested in tracking. And so what we do is, once we get this 3D point which has a reasonably high density, we project this 3D point into the novel view using like standard camera pose, epipolar geometry kind of a thing. And once you get that rendering in the novel view of this point, you can actually figure out, I mean, you can actually probe the SAM model using this novel, there's point in the novel view, and SAM can then basically spit out a segmentation mask of the object of interest. And so that's pretty much it. And so on to experiments, I guess. So here we are comparing our method against state of the art approaches, um, and across different data sets. And by the way, it's important to note here that um, NeRFs are typically trained individually for every scene. So if your scene changes, it has been found that the cross scene transfer of NeRFs is actually quite poor. So for every scene, so each of these data sets has a bunch of scenes inside it. So you need to train a different model for each of those scenes. And what you see is that we're kind of consistently outperforming competing approaches. So, some of these things like, PSNR, numerically you might see that the changes are not that much, but then these are in, log scale. So, even a small change is actually suggestive of a big shift, actually. Um, so here's some qualitative results. So as you see here, the, this is a rendering by our method, and um, the quality is pretty realistic from what you can see. There's no artifacts or blurring and stuff like that. And in particular, if you contrast that against prior approaches, so in the left column here, leftmost column, we show the ground truth. The middle two columns are baselines, and the rightmost column is our method. Like you see, for example, in this toy kind of a setting, that for example, this teeth here is actually more sharply rendered by our method, not so sharply for prior approaches. um, for example, for this toy here, like you see this text region here to be more blurry. That's not the case here. um, or for example, for this human, you see the texture on the shirt is like kind of blurry, or is introducing artifacts. That's not the case for our method. Now, like I said, we can also like our method approach allows for tracking of the scene from novel views as well. And uh, so tracking of, objects of interest from novel views as well. And this table, this is a measure, quantitative measure of the performance of our method in towards that tracking. And and the baseline that we are comparing against here is essentially, this ASA 3D method is essentially like a per frame tracking. It's a state-of-the-art tracking thing, but then it's like the novel view is kind of given to that method, and then that method is asked to track that object. But then our method can both render that object from a novel view and track that object, and we see that we're doing better. The TMIOU and IOU stands for intersection over union. So it's a measure of how accurately the different regions in the scene overlap with the ground truth frame. So if you were to overlay the ground truth frame onto the rendered frame, how accurately is the match happening, the overlaying happening. And TMIOU and T accuracy are just measures for if you are to render in novel time, how accurately is does that work? And again, like this for novel time, there is no baseline numbers, because the baseline is just a temporal tracking method. It doesn't have a 3D notion of the scene essentially. Um, so yeah. So here's like a rendering result by our method, and as you see, this is a rendering of the full scene, and then this is a particular region that's of interest. So the user clicked on this, final car of this train, and so we see that only that particular car of the train is being rendered. Um, yeah. Now, however, one caveat of our method is that it doesn't deal. It's not able to deal as well with sparse views. So if you have a scene captured with very few views, very few cameras, something like 15 cameras, right? Well, then we see that actually there are artifacts that appear, and this is something our method is not able to deal with. And this kind of is like an open area of research, and I invite you all to explore how to fix this. So in conclusion, Gear-NeRF provides a way to incorporate semantic understanding of the scene to perform better rendering of it from novel views. And it is, of course, to the best of our knowledge, the first method to track any object in the scene from any given view, I mean any novel view, at any time. And against all competing metrics, on all competing metrics, and against all relevant data sets, we see that our approach kind of outperforms all competing, I mean, the state of the art methods that exist, and so is the best performing method so far. Yeah, so I guess that's pretty much it. Again, I think I glossed over some of the details. You can find them in the paper, but please do check out the link provided here for more details, including the code and everything else. All right, thank you.
Thank you, Moitreya. Thanks everyone for showing up. So let's open the panel for questions right now. So let's listen the questions from the WebEx. What we have one question from at WebEx.
Okay. Do you want me to read it, or
Yeah, sure.
okay? Let's see. So the question is, given that Gear-NeRF optimizes spatio-temporal sampling based on motion and incorporates semantic information from image segmentation models, how does it balance the trade-off between rendering quality and computational efficiency, particularly in resource-constrained environments? That's actually an excellent question, and it kind of was one of the core motivations for addressing, this problem of novel view rendering from uh, in the best possible way, right? Because uh, the existing approaches, what they were doing is essentially, let's see. Yeah, I mean, whether you consider this method called hyperreal, or you consider these approaches, DNeRF, hexplane, none of them have a semantic understanding of the scene. So they would the best possible thing that they could do is they could just sample uniformly from the scene and render those points, like all of these, like as you can see from these equations here, are taking any randomly sampled point in the scene and rendering it. But then if you do this in a uniform way, then you're not being efficient. I mean, you can kind of do a very coarse level segmentation using sampling using these methods, but that would not be accurate. To be more accurate, you'd have to sample more densely. Now, once you do that for the whole scene, it quickly becomes computationally intractable. So instead, in Gear-NeRF, I mean, Gear-NeRF is just proposing one way to be intelligent about it, which is you look at how things are moving in the scene, and that's what these notion of gears are. And then what we are saying is, oh, like things that are moving faster, they get a more sort of densely learned embedding, or sort of the 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 computational resources invested are more dense, while regions that are moving more slowly are sort of can be rendered with sort of more coarse level embeddings, and you don't need to sample as densely for those regions as well. So that's sort of the idea. I hope that that kind of answers the question. um,
Does that? Okay, cool.
okay.
Please let us know in the chats, like if you have any follow-up questions. Okay. In here we have one question. I think that was pretty on the same direction, which
Okay.
was the question was there can be multiple uh motions in a related in an image, like from a high speed moving fan to a normal like stationary object. So
Hmm.
how do you discriminate these things? So I think this question has already been answered. If you want to add more on this.
I think so too. I mean, in the sense that I think the previous question kind of alludes to it, but the one other point I would add to this is basically the distinction comes from loss. So what we are saying is the hypothesis that we're making is that the loss is a measure of which regions are moving faster. So we start with the uniform assumption that no region in the scene is moving, and then we say that at every step, like whichever region has the highest loss, that is a faster moving region. So we kind of adjust the sampling based on that, and then we see how the rendering quality is with that, as I mean with that adjusted sampling scheme. And then if we still see that there is a high loss, and then we kind of tune the sampling further for that region, and we keep doing that till we are satisfied with the rendering quality. Um, so yeah, I mean, so the loss measure will tell you, which region is moving faster, which region is moving slower. So, yeah.
Hey, I was one of the like participant. I was just watching your presentation. It was a great
Oh,
presentation, Dr.
thank
Chavita.
you.
I have a question. Like, for instance, if you have a fast moving fan, you say like, okay, if you have any fast moving object, you just do a you do a dense you just do a dense sampling there, and that might that will solve your problem. I believe like doing this the reason behind you do this is because you get a better sharp corners and edges like of every of the object, which is like which makes it easy to render. But if this might be a hypothetical scenario, but what if all the cameras are not able to capture the like more than 15 cameras that was like mentioned there? If all the cameras are not able to capture that particular moving object so clearly or so densely that so clearly or so densely that it should be rendered. So like will it be how does that behave? Will it make a symmetric will like when you rotate it around, will it make a symmetrical, or what else, like what is
Hmm.
done if something
Um,
not be captured by all the cameras? Even this might be hypothetical, but something that might happen.
No, it's actually a very major concern. I don't think our approach actually deals with this case. It's actually like if for people who work in this space, this is actually a serious concern, and so there's I think room for work. But I think we kind of are hedging our bets on SAM working, basically SAM, the segment anything model. So as long as we have enough views using which SAM can give us a reasonable enough segmentation of the object of interest, then we are good. But then if there isn't any view which captures that object well enough for SAM to be able to segment it. So for example, like here, for example, if just saying, like if one were to be interested in this pillar that I'm pointing at, um, maybe we only see this pillar from a handful of views, but we don't get a clear shot of the pillar, and we only see parts of it, and maybe Sam just fails to segment that pillar out because in none of the views it's clearly appearing, and so Sam doesn't get a good segment, doesn't do a good job of segmenting it. Then in that case, yes, I mean then it's kind of like all bets are off. So then like the model will kind of either merge that region with a neighboring segment, and then maybe the neighboring segment's motion determines this motion of that part as well, which would not be accurate. So yeah, I think it largely is in the realm of future work. So yeah.
Manshu, does that answer your question?
But if only like if a portion of the image is like captured, but the another like and not that clearly that you can densely pass into it, and you cannot merge it. Like I just want to know how the model will behave in that scenario. Will it like render it like blurry, or will it like be able to like will it try to like generate some of its own something, or like what how it will be, how it will perform?
Um, I see. I guess. Okay. Let me try to answer your question to the best of my understanding. So of course, like it depends on the scene, right? Like I don't think there's a consistent answer, like that it will always perform well or will always perform poorly. Um, but I think essentially, like, I mean, if you have a region in the scene, it will at least be rendered at the sampling resolution of a static region of the scene, because that is the basic assumption we start with, that every region in the scene is static. So whatever spatio-temporal sampling resolution we have for the static region of the scene, it will at least get that part. Now, beyond that, whether that particular region gets sort of a more dense spatiotemporal sampling, that will is entirely dependent on the segmentation working out. So if the segmentation works out, then yes, it will gradually be pushed up in the gear level, and so it will get a more dense sampling of the region, or else it will not. So it really depends on how Sam performs, I think. So yeah, I'm not sure if I'm answering your question correctly, but
No, no,
yeah.
that answers my question. So thank you,
All
sir.
right. Yeah, thanks.
Thanks, Himanshu. Thanks, Mitra. Another question we have. So you mentioned that you're trying to identify key images in a hyperreal, for
Hmm.
example, every 10 seconds. Is there any better approach to that? What if the image might be distorted for every 10 seconds? Like, do you do any pre-filtering, or what are the best, like, what are, what's your approach in that case?
Yeah, so that's a great point, right? So Hyperreal exactly suffers from those kind of issues. So Hyperreal is a prior work, I think, from Meta, and I mean, Hyperreal is not our work, and so it faces exactly these kind of issues, right? If you do uniform sampling, I mean, the frame at which you're sampling may be like, the the interesting events could be happening between two keyframes, or as you say, like, the keyframe could be distorted, or lost, or something like that, or it could be noisy, like the capture of that frame could be noisy. So Hyperreal suffers from all these issues. Yeah.
Thank you.
Yeah.
That's the all question that we
Okay.
have for here. Do we have any more questions? Else we'll end the session. I think, yeah, I know it's Bulldog Bash today. So just to give you a heads up, Mitra, so Bulldog Bash is our orientation concert for the fall. So
Okay,
this is the Bulldog Bash,
sounds fun.
like a city-wide, like every city is pretty much like a fun event. It's like for to give you context, it's like a Durga Puja for this city.
Okay, I see. Okay, that
Uh,
sounds like a big deal then. Okay.
So everyone is pretty much on Friday evening. It happens, so it's pretty much is everyone is gearing up for that. So yeah, I don't see any questions coming up on the channel. So I'll let you go then. So thanks, Doctor. You have any question? Oh no. Okay. So yeah, thanks everyone for showing up, and thanks Mitra for the
Yeah,
session.
thank you.
Uh,
Thank you, Shashwato. It was a pleasure interacting with you all and presenting our work. I wish you all the very best. Thanks.
Thank you. Bye.
Thank you.